In this tutorial, I'm going to go over exam number 6, which is very important because it's going to help you understand difference between mass and weight. It's going to help you understand difference between horizontal circular motion and vertical circular motion. Problem 2, 6, 7, horizontal circular motion. Problem 16 is vertical circular motion. It's going to help you understand Newton first law, second law, and third law. Problem number 12. Importantly, exam number 7 is going to be just like exam number 6. Okay, I'm not going to change anything. So hopefully, if you understand everything I explained in this tutorial, you're going to get 100 in exam number 7, and you have 1 week notice. Hopefully, I'll be able to finish it. I'm actually at NYU. Shubhanu is taking Putnam competition, and Putnam competition is like Math Olympiad, but it's a little longer. It's a 6-hour long test. If you can become Putnam Fellow, Putnam is, by the way, much more prestigious than Math Olympiad. If you can be a Putnam Fellow, 5 students every year become Putnam Fellow, then you can go to any university you want, including MIT, to do your PhD in math. So good luck with that. I gave you a box, 120 Newton. So if you ever want to find the mass of this box, just divide by 10, right? So the box is 12 kilogram. Why you divide by 10? Because acceleration due to gravity here on Earth is 10, negative 10. Okay, so you pull the object, you pull this object by 48 Newton, right? And what I also inform you in the test that the box is moving with constant velocity. Constant velocity. What does that mean? That means the force of friction is also the same, equal in magnitude but opposite in direction, 48 Newton. So you can use the equation that F is equal to mu. I asked you to find the kinetic friction because object is moving with constant velocity, mu k Fn. So mu k is Ff over Fn. Ff is how much? 48 Newton. And Fn is how much? Fn is 120 Newton. Why is that? 0.4. This is Newton, Newton cancel. So you don't have any unit. So this is the answer. Why Fn is 120? Well, pretty simple. It's because the mass is sitting on a surface whose coefficient of friction is 0.4, and this is a 12 kilogram mass, right? So since the box is not moving up and down, Fg is 120 Newton because Fg is mg, and we use negative 10. And normal force also 120 Newton. Problem number 2 is pretty simple. Let's say you take a smaller piece of chalk like this, you attach with a rope, and you rotate the rope, and you rotate the rope like this. Okay, if you rotate the rope like this, it creates the horizontal circular motion. Think about this. If you put an ant on this chalk, right, and attach this is a rope, attach this chalk to a rope, and move this in a circular motion, the ant will feel nothing as long as the speed remains constant. We are also doing the same thing. We are also doing the same thing. We are on the earth, right, which is a little bigger than this, 10 raised to 24 kilogram, right? And the earth is rotating around the sun. perfect uniform circular motion. In this problem, the uniform circular motion, this rotation, the radius is 0.8, and the velocity is the velocity I gave you, that velocity is 6 meter per second. The earth is doing the same thing. This is the earth and this is the sun. So earth moves around the sun. Of course, the radius is little bigger. How much? 92 million miles. So what are the differences between 0.8 meter and 92 million miles? Nothing. The earth moves a little faster. The speed is a little bit bigger. How much? 30,000 meters per second. Is there any difference between 30,000 meters per second and 6 meters per second? No. So if you make the earth very small, right, like this tiny dot, and this is me on the earth, right, 80 kilogram, doesn't really matter. Me become even smaller, like an ant. So if I'm on the ant, right, and that's exactly what is going on. I am on the earth, it is rotating. Why I don't feel it? Because the acceleration is almost zero. Why? This is horizontal uniform. This is called horizontal uniform motion. This is different from vertical uniform motion, which should be roller coaster. We'll do the next time. Vertical uniform motion, the gravity, which would be roller coaster like this. So when you are over here, and when you are over here, and when you are over here, they are the gravity have different influence on your body. But the horizontal uniform motion, the acceleration is almost zero, so you don't feel anything. Acceleration is almost zero. Acceleration of the earth is 0.006 meter per second square. Very tiny, very tiny. You don't feel it. Do we feel anything? Do you feel that earth rotate around the sun with how much? 30,000 meters per second? No, we don't, because acceleration is zero. That's why you don't feel it. Okay, so now what about this one? This one, since the radius is very small, the acceleration will be big. This is also called centripetal acceleration. This radius is so big, 92 million miles. The average distance from Earth to Sun is 92 million miles. A little bit bigger, but I rounded it to 92 million miles, so you can walk around with this information in your brain. Okay, so acceleration is equal to v squared over r. So v is how much? 6 squared. All right, don't forget the meter square. And then r is this one, meter per second squared. Meter squared second squared. And then this is r is 0.8 meters. And that gives you 36 over, so meter square is just 1 meter, so 36 over 0.8 meter per second square. So why this is accelerating? So you on this, okay, if the earth accelerate that much, then we'll all be doomed. The only reason earth doesn't accelerate that much is because the earth radius is big. If you double the radius, what happens? Acceleration gonna go smaller. If you make the r so big, then acceleration gonna go to zero. Okay, and then the ant on this, whatever you call it, shock which rotate around the earth, which rotate well, in a horizontal circular motion. You can imagine, if you activate your brain, then that ant will not feel anything, will not feel that it is rotating. Problem number 3 is an example of Newton's second law. So there is a box sitting on a table. The box weight is 150 Newton. The normal force acting on it is also same, but opposite in direction. The force of friction is 50 Newton. However, the applied force is 100 Newton. This is an example of Newton's second law. Why is that? Because acceleration is not zero. Why the acceleration is not zero? Because there is a net force to the right. How much net force to the right? Net force is equal to ma is equal to net force. So how much net force to the right? Fa minus ff is equal to net force to the right at the x direction. So 100 Newton minus 50 Newton is equal to net force to the right. So how much net force to the right? As you see, net force to the right is 50 Newton. So box is accelerating to the right. How much? Acceleration is net force over mass. This is an example to Newton's second law. Problem number 4 has to do with Newton's third law. What is it? FAB is equal to FBA, but opposite in direction. However, this is not how you say it. Force on A by B is equal to force on B by A, which is equal in magnitude but opposite in direction. So practice once or twice. So you have a lacrosse ball, all right? So this lacrosse ball 0.14 kilogram, mass doesn't matter. This lacrosse ball is moving to the west 7 meters per second. However, that doesn't also matter. Velocity, there is a velocity vector. Okay, now you want to stop the motion of this object. What do? You take a lacrosse stick and you stop it. Okay, so what happened when you block the ball? Well, you don't see what is happening, but actually what is happening is Newton's third law is in action. Whose direction? Of course, this direction. What do you want to call it? You're going to call it force on, this is lacrosse ball, force on the ball, this is lacrosse stick, force on the ball, right? Let's call this ball. Let's call this a stick. Force on the ball by the stick, let's say, is 120 Newton. Doesn't really matter. If this is the case, then the force, let's use the different color. Force on the stick by the ball. So this is ball, let's say blue is the ball. Force on the stick by the ball is also 120 Newton. Okay. If this is to the east, this is supposed to be to the west. Since it is moving to the left, the lacrosse stick apply the force to the east so that the ball come to rest, because now velocity vector and force vector are opposite direction. If velocity vector and force vector opposite direction, since acceleration come from force, acceleration vector is also to this direction. Since velocity vector is opposite to force and acceleration vector, this ball come to rest. Number 5 has to do with Newton's first law. Another way of writing Newton's first law is okay. Law of inertia tells us that if mass gets bigger, inertia gets bigger. More inertia over here than over here. Newton's first law also calls constant velocity. Newton's first law also called when object at rest. Newton's first law also called when acceleration is 0. Newton's first law also known as equilibrium. Okay, these 4 situations I'm gonna quiz you. I did actually quiz you in test 6. Quiz scenario is an example of Newton's first law. An elevator, right? So an elevator moving up but slowing down. So moving up, this is velocity, but slowing down because it has to stop. Is this an example of this is called elevator? This is counterweight. This is scenario 1. Scenario 2, an object sitting on a table and resting. So velocity is 0. And his velocity is not 0. Acceleration is not 0. Scenario 3, an object is moving on a frictionless, no friction, inclined plane. Even there is no friction, the box is accelerating. So velocity is not 0, acceleration is not 0. And the last one is object in free fall. When object in free fall, force is not 0, net force, acceleration is not 0, and velocity is not 0. Okay, so now which one satisfy the above condition to be in equilibrium? Only this one, because acceleration is 0, because net force is 0. And that was problem number 5. So 6 is similar to 2. Why? Because a race car moves in a flat circular path. So flat circular path, and there is a center. So the horizontal circular path is equal to flat circular path. Okay, because both the acceleration due to gravity really doesn't affect. This is not a vertical circular path. The vertical circular path would be like this: location A, location B, and A is different from B. Okay, and the roller coaster would be an example which we'll do next week. Now, let's draw a free body diagram showing two vectors. This is the force and this is the velocity vector. And remember, the velocity vector is normal with respect to the force vector. Normal means perpendicular, means 90 degree. Okay, so when they are 90 degree with respect to each other, then you call it the horizontal circular path or flat circular path. Okay, another example of horizontal circular path or flat circular path would be us. This is the Earth. Let's make Earth bigger. Earth moving around the sun. Okay, because this one has a radius, this one has a radius. This one radius is small, this one radius is big. This one has a force, so the Earth, this is centripetal force. This one has a force. This one has a velocity. This is centripetal force. This one has a velocity. Centripetal velocity over here is, it doesn't matter about how much velocity over here. So these two scenarios are the same. However, if small r causes big acceleration, big R causes almost no acceleration. In fact, the acceleration is almost zero, because this R is big. Okay, hopefully you understand the horizontal circular path and the flat circular path, the differences between these two. Almost number 6, which is almost number 2. Again, horizontal circular motion, uniform circular motion, this is the same thing. So an object moves around a circle with radius r, trying to see by increasing the radius, right? By increasing the radius, how that affect the acceleration. So you see, this is the big R. Let's say this R is 6, this R is 12. Okay, so 6, 12. So 12. So let's say velocity of the object is 12 meters per second, or 24. Velocity of the object is 24 meters per second. And radius is 12 meters per second. It's easy to do the math. So acceleration would be what? Acceleration would be v squared over r. So then 12 squared divided by 6. So 144 divided by 6. And that would be how much? 6 goes to 14 twice, 24. 24 meter per second square. And let's say this case, because we double the radius, and if we double the radius, the acceleration will be how much? V square over r. Again, this is moves with same velocity. So 144 divided by 144 divided by 12, because r. So 12 goes to 14 once, twice. So this is 12. So if you double the radius, the acceleration is halved. Okay. Now, if you increase it to radius, you increase it to only God knows how much. Radius is 92 million miles. This car is here now. All right, the acceleration would be almost 0. 0.0006 meters per second squared. Which one we call Earth? This one. Okay. So hopefully you get the point. So number 8 is similar to number 4. Okay, Newton, third law. FAB is equal to FBA, but opposite in direction. Let's say a 600 kilonewton man. All right, 600 Newton man means only 60 kilogram. That's not me. I'm 80 kilogram. Push a vertical wall like this one. Let's call this one a vertical wall with 100 Newton. So what are you going to call? The force going this direction, which I cannot draw. So force on the wall. All right. So I'm going to draw it to the east instead of drawing inside the board. Force on the wall by Bari. If this is 100 Newton, then force on Bari by wall is also 100 Newton. That is problem number 8. Number 9, in the class, I told you many times the differences between mass and weight. The mass measured in kilogram, the weight measured in Newton. So you can call, instead of, you can call weight you can call FG, or weight you can call mg. Okay. You can only change mass, right, by moving. If your speed goes to c. C is the speed of light, 3 times 10 raised to 8. If your speed is this much or more, then you can change the mass, which is not possible because Einstein proved that nothing can move faster than 3 times 10 raised to 8. So not possible. You can never change the mass. You have to change, in order to change the mass, you have to prove this one wrong. However, weight you can change. For example, me is 100 kilogram. So Bari on the earth and Bari on moon. Bari's mass Bari's mass on Earth is 100 kilogram. Bari's mass on the moon is also 100 kilogram. However, Bari's weight, again, weight has a symbol Fg, which is force. Weight has another name, force, is 1000 Newton. How is that? 100 times 10 acceleration due to gravity. 100 times not 10, 100 times 1.6, and that would be 1600. 160 Newton. You see that the weight you can change by moving a planet that is smaller than Earth. How small? This is 10 raised to 22, and this is 10 raised to 24. You can change your weight by moving to a different, well, the moon is satellite, a smaller mass. You also can change your weight by moving to a bigger mass than the Earth. Okay, there you go. So how can you graph it? I'll give you a few options. 3, 4. All the options comes with mass and distance, mass and distance, mass and distance, mass and distance. So if you are on the surface of the Earth, right? If you are here, and this is radius r, right? Okay, if you're moving up this direction, right? Then what happened? The moon is over here. How much? 3.84 times 10 raised to 8 meter above the Earth, from radius to radius. What happened? Will you be able to change your mass by going to the moon? No. Oh, I didn't give you the option. Let's see how. This is not correct. This is also this is correct because the mass has nothing to the distance. If the Earth moves around the sun in elliptical orbit, elliptical is not a perfect circle, then what is Newton's third law tells us? Newton's third law tells us force on Earth by sun is equal to force on the sun by Earth, which is equal in magnitude, opposite in direction. And so this is force due to gravity. So gravitational force is then attractive. Okay. Now the electric force is both attractive and repulsive, because there are two charges, positive and negative. Okay, the positive charge, all right, and positive charge, they repel each other. Okay, and however, positive charge and negative charge, they attract each other. Okay. So how is that going to go? Positive and negative. Let's see how that attraction goes. I'm going to draw it here. Positive and negative. Positive and positive. Positive and positive repel each other. Positive and negative attract each other. How is that attraction look like? Okay. Fields start, this is called field. We talk about the gravitational force is a field force. Electric force is also a field force, which of course we're going to discuss. Field starts from positive and goes to negative. So this is called attraction. So this is attract. So you see the attract symbol, okay? It starts from one body and goes to the other body, okay? And you see the repulsive symbol. Is it start from the positive and move away, okay? What about the weak nuclear force? Weak nuclear force is neither attractive nor repulsive. What about a strong nuclear force? Is attractive. Strong nuclear force is responsible to keep the proton inside the nucleus. So this is the helium nucleus, strong nuclear force. There is a repulsive force going on, just like this. So a strong nuclear force is responsible to put them together, keep them together in the nucleus. That's why nucleus is stable. So gravitational force is attractive. How do you know? There is nothing moving away from this. Problem 11 is testing your understanding the inverse square law. Which you can rewrite is as 1 over r squared. That's it. Why? Because this is a constant. This is a constant. This is a constant. Constant doesn't matter. This one never can go bigger or smaller. This one, how big that can go, right? And then this one, how big or small that can go, doesn't really matter. This one can go as big as anything you want, any number you want. Okay, all right. So how that affects this? Let's see. If two body, right? The distance between these two body is 1x. 1x means 1x, let's say x meter. Okay, x meter could be any meter. Okay, and the force between these two is the gravitational force between these two is let's say, I don't know, 25 Newton. If you do 4 times the distance, 1, 2, 3, 4, you did increase the distance 4 or 5 times did I mention? I guess 5 times I mentioned in the test. Or 5x. So, okay. So, x, 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 x. So now 1, 2, 3, 4, 5. So then distance between is 5x. And the object is now 5x away from each other. 1x is 25 Newton, 5x is also 25 Newton? No. Is it 5 Newton? No. Is it 1 Newton? Yes. How? Let's use this equation. Let's see whether you can figure it out. G m1 m2 over r squared is 25. Okay? Good. Why? Because radius is 1 square, right? 1 square is just 1 itself. Okay. Now, G m1 m2 over 5 r squared. So what do you get? G m1 m2 over 5 is 25 r squared. You want to rewrite this one, 1 over 25 times G m1 m2 over r squared. And you want to replace this by what? 25. So 1 over 25 times 25. Now you're going to be crouching to jump up. To jump up, you need to crouch. So let's say you crouch from A to B for 0.1 meters. Okay? And from B to C, this is your jump height. Jump height is, let's say, 0.7 meters. And crouch height is 0.1 meters. Your velocity over here is 0. Your velocity over here is, we have to find, and your velocity over here is 0. Vf squared is equal to Vi squared plus 280. So of course this one is your Vc squared, this one is your Vb squared, this one is your Ac, this one is your Dc. This one is 0 because velocity over here is 0. This one is you're trying to find, this one is negative 10 because over here acceleration due to gravity is negative 10. Over here, when the jump height is 0.7, right, the velocity is 0. Okay, at velocity 0, jump height is 0.7. So your velocity at location B is equal to the square root of 14, right? You said 14. The square root of 14 is how much? .74. So your velocity is 3.74 meter per second over here at location B. Find your acceleration. Bf squared is equal to Vi squared plus 280. Okay. Now your Vf is location B, and this is location A, this is location B, this is location B. This is 3.74 squared. This is Va squared, of course, 0. This is 2. Acceleration you try to find at location B. And the displacement between A to B, this is crouching. How long did you crouch? 0.1. Okay, so what is going on? Acceleration is 3.74 squared divided by 0.2. 3.74 squared divided by 0.2, and that is 70. So you want to write acceleration of Josh is 70 meter per second squared, this direction. So that's not what I asked you to do. Many of you gave me 70 meter per second squared. That's not what I asked you to do. I asked you to acceleration of the earth at that time, at that the instant of the time. At that instant of the time, what's going on? Few things going on if you use Newton's second law, Newton's third law. So this is earth, this is earth, this is you, this is you. So Josh, what is going on? This is the force Fg is equal to force on Josh by earth, and then this one has to be then Fg prime, then force on earth by Josh. The Josh is, I believe, let me see how much. Josh is 60 kilogram. So this one must be 600 Newton. So this one must be 600 Newton. Opposite in direction. Okay, now what are the forces acting on it? Josh needs to move up, so he has to push the earth, which he did. F push. What does that mean? Push on the earth by Josh. And if he does that, then this one will F push prime, push on Josh by earth. Now let's separate them. Let's draw the Josh. Only the red vectors responsible to send the Josh to the air. This red vector is F push, and this red vector is Fg. That's it. That's all you need to know. But to put you can also put the earth, and nothing difference, because net force over here would be same as net force over there. Doesn't really matter. Okay, because as you're gonna see that this one gonna be same in magnitude, opposite in direction. So this is the same as this is the same as this, but opposite in direction. So the net force over here would be same in magnitude, net force over there. So it doesn't really matter. If we know this one, we know that one. So let's know the Josh one. So Josh, what's going on? F on Josh at the y direction, all the force is ma. Fp, which is positive, Fg, which is negative, ma. So F push is equal to mg plus a. So F push is m is 60, g is 10 plus 70, 80. So F push is 4800 Newton. Okay, 60 times 80. All right, if this is 4800 Newton, right? If the net force over here is 4800 Newton, the net force over there is also equal in magnitude but opposite in direction. Okay, so now you're going to use Newton's second law of F net is equal to ma. You try to find the acceleration of the earth. So acceleration of the earth is F net over m of the earth. You already found the F net 4800. There is no vector, so you must write the negative sign. Mass of the earth is 6 times 10 raised to 24. 6 goes to 48 8 times. So acceleration of the earth is negative 8 times 10 raised to 24 minus 2. Acceleration of earth is negative 8 times 10 raised to negative 22 Newton. Let me check something. Okay, so now we know that the acceleration of the earth at location B is negative 8 times 10 raised to negative 22 meter per second squared. That's why Josh moved up by 0.7 meter. The earth did not move down at all. Almost 0 meter, it did move down. So problem number 13 is similar to problem number 11, right? Problem number 11, what did you do? This is x distance to body. If the gravity between these two bodies, which is x distance away, is 25 Newton, if that is 5x, 1, 2, 3, 4, 5x distance away, then that would be 25 divided by 5 square, which is 1. 5 is square, which is 1. Why 5 is square? Because 1 over r is square. Okay, that is 11. That was 11, which I went over. Now let's do 13. So this is Earth. There is a radius r, and there is a satellite. And this satellite, the force acting on this satellite is F, and this is r distance away. So this is 1 radii away. So let's solve the problem. F is equal to g m1 m2 over r squared. Now let's see, put 1 over here. F is equal to g m1 m2 over 1 r squared. So F is equal to g m1 m2 over 1 squared r squared. What does that mean? F is equal to g m1 m2 over r squared. 1 squared doesn't matter. And if that is F, then in scenario 2, okay, I hope you can see that. In scenario 2, maybe if I go all the way over here is better, right? Okay. In scenario 2, you have this one now, 3 earth radii, 1 earth, 2 earth, and then one more, one more. So now let's write the radii. This one, this is another one, this is another one, this is another one. Let's count 1, 2, 3, 4. Okay, so if you draw a line, then now instead of writing r, you can write r plus r plus r plus r, or you can write 4r. Okay, so let's see what happened. G m1 m2 over 4r squared. Okay, so we replace r by 4r. We replace r by 1r. Okay, so g m1 m2 over 16 r squared. So g 1 over 16 g m1 m2 over r squared. Remember, we can replace this one by, I think I can write it 1 over 16. We can replace this one by f y, because this one is equal to f. So then it becomes 1 over 16 f. Okay, that was problem number 13. Number 14, which is similar to problem 9. Problem 9, recall problem 9, you have a distance, right? You have a mass. Mass has nothing to do with the distance. Distance increases, decreases, mass never increase or decrease. Problem 14 is the weight. Okay, the weight is mass times acceleration due to gravity. So the problem is the acceleration due to gravity is different in different planets. Okay, even so it's greatly depend on the radius. So g m1 m2 over r squared can be written as 1 over r squared. Okay, because this one doesn't matter because it's constant. They are constant. All right. So how can you draw if you are here on the earth, right? And if you are here at, let's say this is location A, this is location B, this is location C, this is location D. Okay, if you move from C to D, right, how is your graph going to look like? This is R, the radius between C to D, and this is your weight. Okay, so your weight, as the R increases, your weight going to be almost zero. I'm gonna this is asymptotic, but I think I can do better. As the distance between C and D increases, what happened? Your weight goes to zero. That means if you are infinite distance away, which is D, then your weight is almost zero. And when your distance is at C, all right, at C, then it is of course 9.8. Okay, so that's that. However, if you are moving from B to D, for some reason you are at B, then the graph would look a little different. Then the graph would look, this one is C to D. This one is B to D. From B to all the way to the D. So let's first draw the radius. From B to C is the radius of the earth. B to C is the radius of the earth. And B to C is 6.37. 6.37 times 10 raised to 6. And this is your mg. At B, location B, at location B is 0. Acceleration is 0. At location C is 9.8. Okay, this is location C. Well, here, this is location C. This is 9.8. However, here, this is location C because we started from location B. B is 0, C is 9.8 times mass, of course. You know what I mean. And then, of course, this one. From location C, this is location C to location D. Okay. When I only put this one, it makes sense. When I put both of these, this makes even more sense. All right. Okay, that was problem number 14. Problem number 15 is pretty easy. An object moves for 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. And if x-axis is time, y-axis is distance, displacement rather. Its displacement is 2 meter, 4 meter, 6 meter, and 8 meter. Okay, and this is what is going on at 0 to 2 seconds. It moves with velocity v. 2 to 3 seconds, it moves with velocity 0. 3 to 4 seconds, it moves with acceleration a. And 4 to 5 seconds, it moves with acceleration a minus. We want to find the velocity at 4.5 seconds right here. If you draw a tangent line, how can I draw it? If you draw a tangent line, you already know the slope of the tangent line is the velocity you are looking for. The slope of the tangent line would be negative v. We are looking for the magnitude. We are looking for the speed because we already know the direction at 4.5 seconds. How can we do that? It's pretty easy. So we're going to convert it to VT graph. So let's convert it to VT graph. 1, 2, 3, 4. 1, 2, 3, 4. 1 second, 2 second, 3 second, 4 second, and 5 second. And let's make sure that this is your time and this is your velocity. Velocity from 1 to 2 seconds is 4 divided by 2 is 2 meters per second. Let's put 2 over here. Velocity from 2 to 3 seconds would be 0 divided by 1, which would be 0 second, 0 meter per second. Velocity at right here is 0 over here. Velocity is 0 over here at 3 seconds, and 3 second velocity is 0. But there is a big transition at 3.00001 second, right? 3.003.0001 second. Velocity not 0 because object is speeding up. So there is an acceleration. How big the velocity, we don't know. So we're going to just write v. If this is v, this is just negative v. We are focusing on this one. Why is that? Is because this is the negative slope. Because at 4.5 seconds, all right, the slope of this one would be negative. We already know the direction. Now we're going to just find the speed. All right, so since we don't know how much velocity is this one, we know it's a big amount. So, however, the good thing is we know the velocity over here, which is 0. And if this velocity is v, this is negative v. Okay, so we can just make a diagonal line. And what we know, we don't care about that. Anything else we care about right here. Like this one. Maybe I should use the red. This triangle, this red triangle. So the red triangle is what? A red triangle is area is half BH. The area is displacement. Half B is time, H is velocity. Velocity we know that is at 4.5 seconds. Displacement is what? Displacement is equal to dF minus di. dF is how much? 4 right here at 5 seconds is 4. At 4 seconds, however, it is 8. So displacement is negative 4. Negative 4 is equal to 5 minus 4 is, of course, 1. Velocity is then negative 8. Yeah, negative 8. So what do you have to do? Use the midpoint formula. Velocity is velocity final plus velocity initial divided by 2. Velocity final right here is negative 8 plus 0. Velocity initial at 4 seconds divided by 2. So velocity is negative 4 meter per second. Okay, there you go. Problem number 16 is a different type of problem. Is something called vertical circular motion. Problem number 2, 6, 7, horizontal circular path like Earth moves around the sun in an almost elliptical circle. This is not a circle. This is not an ellipse. Okay. Okay. Now, problem number 16 is vertical circular motion. An example is roller coaster. And roller coaster is at this location, and I ask you to find the force and velocity direction, and they are 90 degrees with respect to each other.